In this tutorial, we will create an HTA that's going to align geometry along the polyline inside Houdini and Unreal Engine. At the end of it, we should have something like this, HTA with a bunch of options and lots of options for us to improve it and expand the functionality of this tool. But at the end of it, it's going to be a good starting point. You can see that we have ability to do a random noise or pattern geometry alignment. So you can see that I have at the beginning of it this geometry that I got from Unreal Engine, like this. What I have done is I got also polyline from Unreal Engine, like this. With a bunch of options, I have ability to copy it to the curve, like that. And then I can change the pattern that I want to, let's say I want to randomly align the geometry along the curve, like that. Then I can change the random seed of it. I can also use a noise, and also I can use a pattern to align it. Let's use a pattern to show how it works. So with pattern, we will create a tool that's going to automatically fetch the name of these pieces that we get from Unreal Engine or from Houdini, and we're going to get the name of it, and we can basically then initialize the pieces like that. We're just going to use a Python. It's going to show the piece name and the piece width, and then we can be able to also to change the width of it for the different effects along the curve. But since we have these, we can go ahead and let's say I want to create a pattern with the geometry 1 and 2. You can see we have now geometry, the same geometry is copied along align the curve with this pattern, like that. We will have also option for us to create a straight edges curve like this. Let's say we want straight edges like that, and a bunch of different. We'll be able to randomly delete, random deletion like that, random pitch, yaw, and roll amount to make different effects. And we don't have to use even we don't even have to create something like fences. We can input any geometry that we want. Basically, it's going to scatter it along the curve. So let's go inside Unreal Engine, and if you have Unreal Engine's Houdini session sync, it should basically, the results should be already visible inside Unreal Engine. And this tool doesn't have to be limited to the fences. You can basically scatter any geometry that you want with very easy controls. You can go inside our in HDA, basically just go ahead and drag a geometry that you want to scatter along the curve. So let me clear this HDA. Let's clear this out, and I have basically some meshes that I got. I just want to scatter them. I can just take these, maybe something like this, and drag them inside the input. And the HDA tool is going to take care of it. It's going to scatter these geometry along the curve, like that. So there's a lot to this tool, so let's get to it. Let's start by pre-processing geometry that we have gotten from Unreal Engine. So you can see there's a couple of attributes, and one of them are actually Unreal input mesh name, which is a string with 5 unique values, which is exactly what we want. Because of we know that we have we referenced inside Unreal 5 input meshes. Basically, every one of these is going to reference its own static mesh. So it's going to be our piece attribute that we're going to use for the further processing of the geometry. So open up the type properties and let's start adding some parameters. So we can add some strings. So I'm going to call this piece attribute. So for these, I like to call them abbreviate attribute as attrib for the name of it, or name of the parameters. But for the label, let's do it with the full name. So we need our piece attribute that's going to select from the HDA. Then we want to create an internal ID integer value, which is going to be a unique identifier of every piece, every unique piece of this geometry for the pattern creation. We're basically going to be able to write pattern like 0, 1, 0, and then it's going to basically select the ID attribute that's called 0, 1, and 0 for the pattern. So we don't have to write out long names of the geometries. We need our ID attribute, and then we also need the internal name of this geometry. It's basically going to be this input mesh name, the very last part. You can see that it's a crazy Unreal name. You can see at the end of it, there is a name of this static mesh, which is S modular safety rail kit, and then just a random words load or one. So we want to extract this name from this path, because we're going to use this as a label for us to from HDA to change the offset this geometry. Basically, if you want to, let's say you want to move this geometry, maybe the pivot doesn't align correctly, we can basically change the width of it after we have set its bounding both width. So I'm going to explain it all, but basically right now we just have to worry about creating two new parameters. I want to create internal ID attribute, internal ID attribute, and then just and then I want to internal name attribute. So this is going to be, or we can even call this like a label attribute, maybe. Name attribute. So this is going to be very useful for later on. So we have now two parameters, which is good. We can just put it on the side for now. Want to now do it. Actually, let's do this also. Let's just copy this Unreal input mesh name, and let's set up the defaults of these parameters. So the piece attribute, for now, we're going to use it manually. We can just go to the channels and use this as a default value of this attribute, Unreal input mesh name, like that. For the internal ID, let's say our mesh maybe already has an ID attribute. It's a good idea to basically underscore ID, something like this call, and then internal name, like that. And if you apply it, and you go to the parameters, you can see we have automatically set these names, which is good. And yeah, now we want to go ahead and set these two attributes up. So we can put this on the side. For each, we can put it for each number because we're going to use this iterator. So let's connect this. Let's give us a little bit more space. So it says here, I'm going to put that attribute triangle. I want to make sure that I run over the primitives. So, and for the merge, I want to do it by pieces or points, and then I want to make sure that it's at the primitives, and I want to reference this parameter, which is our HDA piece attribute, which is see if it's 0, it actually starts to cook it. Just exit it, and let's disable it so it doesn't try to run it. So it's going to be chs dot slash and piece attribute should be something like this. You can see, make sure that you are using this I think it's, I'm not really sure what's the character ampersand. It's basically the next to the one on the left on your keyboard. It's basically saying that even though this is a string parameter, I want to reference a channel from the whatever the channel I want to reference. So the piece attribute is set, and if it's correctly set up, it should be 5, like that. And then inside this wrangle node, let me open this up inside the code. So what I want to do is get the name of the parameter I wanted to use as an internal ID attribute. And this is where my tool is actually going to come in handy. So for me not to go back to type properties, what you can do if you're using one of my tools, you can just go ahead and copy this copy parameter name. And if you copy this parameter now, you can go ahead and let's say, so the parameter is going to be string. Let me close this. It's going to be string ID. Attribute is going to be chs and dot slash because one up, and then we can just copy this that I just created. So the internal ID attribute is copied. Now I want to reference the iteration. So this is where our counter node is going to come in handy. So I just connect it to the second one and go inside here, and there is going to be integer. Let's call this ID. So it's going to be detail attribute. Detail geometry is going to be 1. Attribute is iteration. And then we do not need that one, like that. And now what we're going to do is just set this attribute. Basically set this attribute, set this ID attribute at the ID name. So go set prim attribute. Name of it is going to be ID attribute. Primitive name is add prim num. And the value is going to be ID. Like that. And if you have correctly set this up, you can see it should be basically our ID should be set up like that. Detail iteration looks good. And at the end of it, you can see we have our ID attribute 0, 0 to 4. And what's good about this, that if you want to change our internal ID attribute name, you can see I write it out and you can see it has updated. So this is basically prevents us from hard coding attribute names that we may have to change later on. And whenever you're doing this, make sure that you save constantly because sometimes it's basically likes to crash. So we have this, and now I want to set our name attribute. So the name attribute is going to be a little weird because we're going to use basically the same piece attribute that is inside here. So it's basically, this is the safest way for us to do it because we know that this name attribute is exactly 5 times, also 5 times, and it's we can safely create it as also as a name attribute that's going to be also as a label because this input mesh name is actually where the name of this where it's actually stored. We just have to extract the name of this mesh name. This is where we're actually going to use regular expressions. So what you can do is go ahead and create another primitive wrangle, connect this up, and I want to do also, again, I want to reference my piece attribute. So the piece attribute is the basically piece attribute is going to be whatever the attribute that you want to extract it from. So let me do this like this. So let me open this up, set code, just close any of the old ones, like make this a little bit bigger. So first of all, I want to go ahead and copy the piece attribute parameter, and let's start by string piece attribute chs, like that. So this is the attribute we want to extract the name out of, is our piece attribute. And then I want to get this attribute, and this attribute is going to be string, let's call this piece attribute name, because we want to actually, now this is just a name of the attribute, and now we actually want to get this attribute. Piece attribute is going to be prim piece attribute name, and the prim num at prim num. For us to actually extract the name of this mesh, we're going to use regular expressions, and if you're not familiar with them, just Google it, and it's going to give you the what's the regular expression is. Regular expression, regex, is a sequence of characters that specifies a match pattern in text. And if you go to this awesome site, which is regex 101, you can basically just test out different kind of expressions that you want to test out, and if you want, and what kind of what you want to match. And we know that we want to match our input mesh in Unreal input mesh name. Just copy it and go inside here and paste inside here. So with the this is what you want to match, and this is where you can create your regular expression. And actually I have created one already, and I'm going to run through it a bit. And basically this is my regular expression. It's going to extract the either name, basically anything after the dot, or entire string. So let's see, I also have, and if I go and write something like mesh 101, something like this, if the name is basically the if it's convenient, if the name is regular name of the mesh, something like on a disk, it should be probably only from the strings and also maybe from the underscore and all of this. So this is still going to be matched, but it's also going to match the crazy Unreal mesh input name because of this expression, which is basically saying start at this. Basically, let's go through this. You can see it's actually also gives us all the what it actually does, but I'm just going to quickly go through it, what it actually does. So start at this at the beginning of the string, which is basically here. Match any word character, which is basically upper and lowercase a to z, and any number, and also underscore. This is why the underscore also gets matched inside here. Basically, if you catch this, this is the match, which is, you can see it's a highlighted match in a blue. But you see this only part would not match this string because of this dot, because dot is not actually a name and word character, which is a matches any word character. It's basically it's not included into the allowed characters to match. So this is where this alternative comes in. Basically, just like in programming, it's an or statement, or if this is a if this is a positive look behind. Basically, if the positive look behind is a dot character. So if this match and then just match everything until the end. So basically, if it sees the dot before, basically if it sees the dot, anything after the dot is going to be matched if all of them are also named characters. And in Unreal, these always should be word characters. It should be matched. We can even use basically this one, basically the same dot, something like, I think it should work. Word plus, because of the something like this, to basically match also the same thing. And yeah, so this is also going to match like that. So what we can do is copy this regular expression, go inside your wrangle, and then we can just use a string, use I'm just going to use this a name like that, and we can re find. Then we have to give it our regular expression. We can just copy it, and the input is going to be piece attribute like that. And then we can just set prim attribute. The name is going to be our piece attribute. The name is actually going to be, well, we have not actually specified the name, so this is probably something that we also want to give it as a parameter. I'm just going to, for now, let's call this a name. Prim num is going to be prim num, and the value is going to be name, just to see if it works. So you see, it's not doesn't match it because of the probably because of it's not because of all of these crazy characters. It's a good idea to create it as a raw string. You can see it's now actually going to match only the last part of it, just like in regex. Basically create it as a raw string, so it doesn't include any of these escape characters. It doesn't mess up all of that. As a raw string, it's going to match all of these. And this is good because if we have a name attribute, which is a regular name, just from the strings, it's also going to match it. But also I want to probably go ahead and create the internal name attribute also as a parameter. Actually, I do have an internal name attribute. Uh, I'm just not referencing them inside here. So let me just copy this parameter name. Let's call this name attrib name chs dot slash internal name attribute. And then we can just copy it instead of hard coding its name. We can just do it like that. We can name and you can change it. You can see like that. So yeah, we have now created our ID and the name of it. So this is going to be two very valuable attributes that we're going to use later on. And now what we're going to do is create our dictionary that's going to hold the identifier, basically the name that we just created from here. That's going to basically the dictionary where the key is going to be the name attribute that we just created, and the value is going to be the width of this geometry that we want to instantiate along the curve, because it is very important for us to know it, because we want to know where do we want to put our points when we are actually instantiating it. So put down a wrangle node. Let's put it on a detail, and I want to be able to select the axis of the width of the size of this input geometry. So by default it should work best with along the x-axis. I want to get how long it is along the x-axis, but there's probably also a case for us to give it an option to measure it along the z-axis. And one thing to note that z and y-axis are actually inverted inside Unreal Engine. So, but x-axis is also going to be the same. So it makes sense for us to use the x-axis on both of them as a width detection for us to have a little bit easier time to understand all the axes. But you can also use the other axes, but you just have to know the naming convention of them. But that being said, all I want to do is go ahead and create a button strip inside my HDA. I'm going to call this size axis. And then inside menu, I want to make sure that it's a replace field, because we can select only one x, y, z. And 0 is going to be x, and 1 is going to be z. Yeah, so this is good, applied. And now we can select what's the size axis. This is what we want to actually go ahead and reference inside our wrangle. Let's just open this up. Inside here, let's go to integer size axis equals chi dot slash size axis. And I want to also get our name attribute, internal name attribute parameter. So let me copy the name of it. String name attribute is going to be chs slash internal name attribute. Right, we have that, and I want to get the all the unique values of these Basically, since we are not running over every primitive, we want to just get because we do not need to. We can use it. Well, I'm just going to show it. So what you can do is actually create a string. Let's call this unique names equals, and there's a function unique vals. Geometry 0 attribute class is going to be prim, because it's going to only work on primitives, since all of these attributes are primitive attributes. And attribute name is going to be our name attribute, and this should actually right, it's an array, so we have to make sure it's a square bracket. And to test it out, what you can do is print out the what we have gotten. Unique, I think that's correctly Helped? I think so. But if you have done it correctly, it should print out on the console something like this. You can see we have all the unique values of this of our name attribute, so that's good. And now I want you just go ahead and for each loop string name, so unique names, we can use a unique name, so it's make it a little bit more consistent. And now I want to create a group selection from it. So basically to get the want to get the bounding box, you can use a bounding box function, which is a get bounding box size, something like this. And there's actually option for us to use the primitive group also. So what you could do is actually create a primitive group string, and we can use it as a separator on what bounding box to look for, because right now the input geometry is all of it is together, and if you call the bounding box on it, it's going to just get the bounding box of entire geometry. So let's create a string selection of this group. Let's call this string, let's call this name, let's call this like a group name, and it's going to be basically add a name attribute. You just want to use a plus signs to connect all of these together. So add, first of all, we need to use add, and make sure that you put it inside quote, because this is a string, plus the name attribute, and then we want to use the unique name, which is a unique name of this one, like that, plus a unique name, and this should be printf. Let's take a look at it, how it looks. Group name. So yeah, so you can see it basically gives this string, and this string can be used as a actually we have to use also equals. So also use plus equals also inside quotes, like this. Basically this string, if you put it inside any of these like a blast node, we just created primitives like that. You can see the string is valid as a group selection. It's going to delete everything except for that one. And it's always, it means that this is also valid for the group selection on the bounding box function. And so what to do is get the bounding box. Let's call this piece bounding box. Get bounding box size is going to be 0, and primitive group is going to be group name, like that. And then I want to start referencing this size axis. If size axis basically 0 was the equals 0, that means the x-axis. What we're going to do is create our dictionary. So first of all, let's create our empty dictionary before the for each loop. So it's going to be dict. Let's call this with dictionary, and then we can just use with dictionary, add a new key for it. With dictionary, so the name of it's going to be our unique name, as a key is going to be, and its value is going to be our bounding box x. So basically, because of the 0, if it is 0, that means the x-axis, and in the vector xyz, that means we have to use a piece bounding box 0 index, like that. And then we can basically use a continue. And basically, if it's 0, it's going to hit continue and run the next loop. So we don't have to use for the second condition, which is basically the z-axis. We don't have to use else statement, because else statement is with xy, so it would be 2, because xy and z, because the index would be 3 for the z-axis. because this continue would be hit it and would go to the next loop, and it would never hit this one like that. That's why we can use it without the else statement. And once we have done this, we can just set our set detail attribute. I'm just going to call this with dictionary, same as its variable, like that. And let's take a look at it. Let's inspect it. So you can see this looks correct. So we have our key, which is the name of it, and then the sizes of it. So the sizes seem pretty small because of this. So we have probably because of selected the z-axis. So let's select the x-axis. Let's watch it again. Okay, this looks much closer to correct. You can see 3. You can see that most biggest piece is going to be 3, and these sizes look actually correct. So yeah, we have now created our width dictionary. And one more thing I want to actually do is, for the future, I want to use also the maximum index piece, which we can actually set it from here. Basically, the max piece index is going to be used in a couple of places for us to know how many unique pieces actually we have. What's the maximum index? Because it starts at the 0, we're going to have to need to calculate some of these parts. So set detail attribute. So it's going to also 0. The name of it's going to be, I'm going to call it max piece index. And then I just want to use a length of the unique vowels. Unique names. That. You see we have 5. And since you want to use, let's start basically start with 0 as a counter, and the maximum piece index is actually from our ID is actually 4, because we start at 0. We can just subtract 1 from it, like that. Because the length of this array is going to be 5, because of the 5, including 0, 0, 1, 2, 3, 4, and 5. That could be 5. But we just want to get the maximum index of our ID attribute, which is going to be 4, like that. So this is basically set up correctly. Yeah, so we can close this one for now. We have created this one, and now I want to be able to offset our point. Basically, we want to if we want to if our pivot, or want to do a little bit of overlap of the geometry that we want to instantiate, I want to make sure that I can basically manually override the sizes of these bounding boxes in this dictionary. So let's do that. So let's start by creating a couple of parameters. So actually went ahead and made a couple of them. So inside this each day, what I did is basically create a button that we're going to later on fill with the use a little bit of a Python to initialize the pieces. And then I want to create and I created the multi-parameter block, which is called pieces. It's going to be piece name, which is a label parameter, and the width of it, basically width offset, that we can manually create make pieces a little bit smaller or bigger with it. And in the end of it, it should be look something like this. We have our piece name that we're going to get from our extracted name attribute from this one, and then the width offset that we can manually edit our dictionary we just created. Let's say I want to make this piece overlap with the next one, like that. We can use manually override the width of it. So let's do that. Let's create a wrangle node. This wrangle, make sure that we're running over the points detail. So first of all, let's get these attribute. I really am interested only in this width dictionary. So dict, let's call this width dict. And one weird thing with dictionary is that we cannot call already with dictionary and call the detail attribute get function, because it doesn't like that. So that's why you just have to use like this. You have to do it in 2 lines. With dictionary equals detail 0, detail attribute is going to be with dict, going to be ignored. And just to check it out, you can print it out. And you see we are getting our dictionary like that. And now I want to loop through the dictionary and get my multi-parameter of the width offset, and I want to add this offset to the current dictionary. So this is where the let me actually keep this one open. So what I want to do is run through the, so we cannot natively run over the dictionary, but we can use a keys function to run over the keys of the dictionary. So what we can do is for each, let's call this int. So this is going to be index, basically the ID. Basically this is going to be also equivalent to the our ID attribute inside here, because of the ID and the name, and the name actually matches with every geometry. So this is going to be index, and then going to be string. Let's call this width key, and the array is going to be keys of our dictionary with dictionary, like that. So now I want to get the float attribute of the current width is going to be our let's call this piece width equals width dictionary, and then in square brackets our width key, like that. And I actually think it actually doesn't like this one because of the basically, right, it doesn't like float dictionary. We have to do it, I think, a little bit differently. So basically we have to declare a float before that. With dictionary it's a little bit weirder, and then we have to basically say that this float is actually my bad, it's actually not with dictionary, actually with key. Okay, you can just go ahead and print this out. Piece width, and we're getting our width correct, so that's good. Okay, we have gotten our width. Now we want to get the parameter, multi-parameter block that corresponds to this piece. This is where actually going to start referencing our, we want to also reference our multi-parameter folder, which is the name of it is the pieces. It's going to be basically integer. Let's call this piece multiparam equals chi. It's an integer, which is basically saying how many multi-parameter we have, and this is going to be used as a, basically we probably don't even need to use it because we're using our index. We're basically we are assuming that we have basically, actually let's not use this. So actually let's do this a little differently. So basically what we're doing is we are assuming that this multi-parameter, we're going to set it up with Python, is actually correctly set up to represent the amount of pieces that we have in a dictionary, because we're running inside here and not over the multi-parameter count, which we could have run through the for loop using this piece count, like that. But since we're going to initialize for every piece one multi-parameter, we can run through the keys and then reference the parameter from the keys, basically from the keys index, like that. Because of these offsets are just a offset with the dot at the end of it. And one thing I want to also make sure that our multi-parameter blocks actually starts at the 0. because the for each loop index starts at the 0. So right, let's start by getting this parameter. Let's actually try to what is it, control. Okay, never mind. Let's get this parameter. Actually, it's going to be float, so the current parameter value is going to be piece offset. We're going to have to use a chf dot slash. Then we just want to add printf. Printf is going to basically name of the parameter, which is in my case is width offset. Width offset, and then we have to use a percentage sign and I as integer, and want to replace this I integer with our index. So this is dynamically referencing multi-parameter block parameter like that. And we can actually print it out, take a look if it actually works. Piece offset, that. So it's 0, but not all of them, because one of these parameters is actually 1.7. You can see we are getting these correctly. And now I want to just update our width dictionary with a new offset. Basically, we have our offset, we have our current, and then we just want to add these together and set our width dictionary. So basically, width dictionary, the width key, current key equals, then we just want to piece width plus a piece offset. So this is going to update our dictionary, and what we can do is at the end of it, for each loop, we can just set detail attribute name width dict. The value is going to be width dict. Mode, we don't need that, but basically we have set overridden our attribute with our new widths. If you take a look at it, and if you start to modify these, you can see the widths of it are changing like that. And now let's actually create the actual logic that's going to instantiate geometry along the curve. So what I have is I created a test curve, which for now we're going to assume that this is maybe our curve that we get from the Unreal Engine, which is a smooth curve. Now let's say I want to instantiate randomly my geometry across this curve. So what I'm going to do is actually go ahead and use the snipping tool. Let me actually draw this out. So what we want to do is to demonstrate how the tool is going to work. We're going to get the length of this curve. So let's say this length is maybe like a 20. So in Houdini it would be meters, so 20 meters long. And then I want to basically get a curve. Basically I want to create a straight curve. And let's say I have, and then I want to start randomizing points. So I want to start randomizing points and getting values from my dictionary, which is inside here. So in my dictionary, I have random values and I have a length of these bounding box size of these geometries. So let's say I have randomized piece 3, which is 1.6. So that means 1.6, the next point that we're going to instantiate is going to be 1.6 distance to the next point. Let's say this one is instantiated at a 3. So that means this is going to be now 3. Length of it is going to be 3 to the next point. And then let's say I instantiate 1. So this is a 1, 3, 1.6. You can see that basically we randomize it, and that randomization determines the how far the next point is, like that. So this is why it's important for our geometry to be aligned with basically to the positive axis, like that. So this is one thing that we're going to pay attention when we are actually instantiating geometry. But this is the basics how the curve is going to be created. So we don't want to try to figure out where this curve is going to be already curved this like this. So this would be maybe not too efficient for us to do that. What we want to do is create this curve straight, and then we just want to align it along this path. And we're going to do this with, let's put down a polyline. It's actually a line stop. So we have a line. We're going to rotate it along the x-axis. Make it length maybe 10. Add more points. And what we can actually do is Houdini has a path deform node, which is exactly for this kind of instance where we have my line, which requires geometry to deform, and then the path we want to deform it to, which is our unreal line, like that. You see right now it looks incorrect, but because our we're going to create our line along the x-axis in this path deform, we have to go to the capture and align and put it to the forward vector as an x, like that. And you can see we are starting to deform this curve along this line, but you can see our input line is actually a little too short. So what we can do is make it longer. You can see it's going to along, and once we have exceeded the length of our input curve, unreal curve, it's actually going to just go straight or onwards. You can see deformation. So this is maybe not the default value that we want to do, default behavior. So what you can do is actually clamp this curve to the actual length of the deformer curve, which is inside here. Map length using fraction of curve length, like that. It is actually going to whatever our point, whatever the input curve is length is. Let's say our is like 100. At the end of it, it's still going to be basically clamped to the length of the input curve that we want to deform to. So this means that we want to make our curve something that is very similar to the length of this curve, and then we can just deal with the discrepancies between the sizes of the between the new sizes of the between the basically sizes distances between the new lines with the scaling. Because once we have aligned this curve, our instant point curve to the path deform, the distance between these points will be a little bit offset. It's not going to be exactly this exactly the bounding box sizes of this geometry, because of all the curvature that it has to take in account. So it's going to be a little bit, usually a little bit smaller or bigger. So this is where we actually want to go ahead and scale our geometry, and usually it's not very visible, the scaling, but this will make sure that our geometry is correctly aligned. Each basically the next one, there's not going to be weird gaps between geometry. So that's why we're doing this with this path deform way. And to do this, let's start creating this setup. So first I want to do it randomly. So I just want to create like a random, basically create a seed parameter. It's going to randomize the pieces. It's going to be aligned along the curve. So this is going to probably be the most straightforward one. So put down a wrangle node and connect it to the second input, because we're going to create our points. We don't want to get our geometry along with it. And then I also, for my sample, it's just a simple curve. I resampled it and I put down a measure slope. And in measure slopes, I just want to get the total perimeter of this. So measure slope, perimeter length, basically just a total perimeter. You just want to get the length of this polyline, which is 17. So this is basically the maximum. Basically, anything that we do not want to exceed. So we can basically do not want to exceed this polyline to be more than 17. So once our point accumulative bounding box size of the points that we create is going to be bigger than 17 of this curve, we say, okay, stop creating new points, and now we want to deform it to this curve. This is going to give us the best results and least amount of deformation when we start to instantiate this geometry. And so to get this, I actually want to go ahead and connect it to the third input of this wrangle node. So inside here, let me open this up. Let's close the other ones. Let's start referencing. So dictionary, I want to get my width dictionary. Width dictionary, which is detail 1. And then I want to get the again the parameter, total parameter. It's going to be a float. Let's call this total parameter equals detail. It's going to be 2. And then the attribute is going to be total parameter. So we have these 2. And then I also want to set some of the attributes on newly created points. So I want to get my internal name attribute from my HTA. So I'm going to go ahead and copy parameter name. I want to get the internal name attribute. Let's call this name attribute equals CHS, like that. And now I want to create a seed parameter, float seed CHF. So seed attribute can be stored on this wrangle node, that's fine. And I want to get the start position of the point that we're going to create. So the start position is always going to be at the origin, so at 0. Float start position equals 0, which we're going to make it bigger by looping. So we have this, and now we want to actually get the keys of our dictionary. Because of the keys, our dictionary holds the widths of these values, of these pieces that we have imported inside here. So I want to get the keys of the dictionary. So let me get this string. Let's call this width keys. It's going to be an array. There's keys with dictionary, like that. And I think we have everything set up. And now what I want to do is actually go ahead and disable this wrangle node, because we are going to use a while loop. So while loop, you have to be very careful, because if this condition, when basically in these brackets, it has basically you have to give it a condition when to stop this while loop, and if it's not being basically fulfilled, it's going to keep looping, and basically it's going to stop everything inside Houdini, and you have to mash escape key. So for now, since we're not immediately iterating and updating this while condition to be false at some point, just disable the wrangle node, and let's write this out. So first of all, also I want to make sure that our dictionary is actually something that we can use. So what I want to do is take if, because if we are getting a dictionary with no keys, that means we cannot do anything, and that also can lead to the infinite loading of the wrangle node. So if length of the let's do this with dictionary smaller than, well, we can basically equals 0. Basically if it's not, well, wait, so if it's not 0, that means we want to continue, right? And this while loop can be inside, like that. So this while loop is going to be basically want to, if the start position, which we are going to increment inside our while loop, is bigger than the total length of the total diameter of our unreal curve, then we want to stop creating new points, like that. So this is my condition to stop the while loop. So in this while loop, I want to create a new point, new pt. It's going to be add point 0, and the point number, basically position where to create it. And then at the start of it, we can just put it at the 0, 0, 0, because we're going to put it basically going to change the position of it this point later on. But we need to dereference the point because we're going to set the attributes to it. So it's a good idea to just create a point right now and then move it later on. And now I want to randomize a randomized piece from our dictionary. Basically get a random key, basically get a random piece from our dictionary. So this is going to be pretty simple. So integer, and for the randomization, we're going to basically get the random index for the keys. So this key is an array, and we can get any key using an index of it. So basically, index 0, 1, 2, 3, we can get keys like that. So in this case, since all of these are ordered, we know that in with key, index 0 would be our mesh 1 is it 1 1, with 1 is going to be this, 3 this, and last one would be this with the indexes. So we know it has a perfect match between them. So it's kind of a, we are not determining it manually, it's just a way that geometry is processed, and we know it's going to, in my experience, it should be just work just fine. So I want to get the integer. We're going to call this rand piece, and it's going to be a rand function. So we want to give it our seed, and now I want to give something that's going to change in every while loop. And in this time, we can basically either give it our point, because for every loop it's going to be a new point, and it's going to be a new value for this point, or we can give our start position as a, since also in every while loop we're going to increment our start position for our point to be basically moved along the x-axis. So I'm going to use start position to make my random seed for every loop different. But there is a problem because our rand function gives only from 0 to 1 value. So what I want to do is multiply it by length of the width keys. So how many keys we have, we're going to multiply it by that. So this is going to give us values between, now if we have 5 keys, so basically between 0 and 5. And we actually do not want to 5. Well, it's very real. I don't think it's actually will go to the 5. It will give like 4.99, I think, something like this. So this is still, we do not want to, so this is going to be a float value. So what I want to do is actually cast it to the integer. And what's good about this casting to the integer is that it's actually going to cast it to the lower integer. So let's say our value is 5.4.9. It's actually going to cast it to the 4, and 4 index we have. We do not have a 5 because our index starts because of these width key starts with a 0. So we have, even though we have 5 values, we start with a 0, so we have only 4. Maximum index random piece would be 4, like that. So yeah, so it doesn't like, so let's take a look at this. I think that's correct. So integer cast its integer and then multiply by length of the width keys. So I'm going to assume it's correct. Oh, right, we need this. So let me just start writing the next part, and then we just take a look at all these errors. It doesn't like this line, so let me take a look at it. If it looks good, so random looks good, multiplied by length with keys. Probably seeing something super obvious that's not correct. It's okay, let's just write this everything out. So now that we have gotten our random piece, we want to get our get from the dictionary the piece width that we have randomized. Float, let's call this rand width is going to be our width dictionary, and then we're going to use our width keys string array, and then we have to do again square brackets and give it an index that we just randomized like that. So this is our random width, and what we want to do is go ahead and add this random width to our start position, so that in next loop our point is going to be copied right where the last one ended, basically the right where the last point's width basically ends. So just start position plus equals random width. Let me actually go ahead and enable this node. Okay, it doesn't actually now show error. But if you have done this, if we are starting increment the start position, it should be saved to actually go ahead and enable this wrangle node, because we should be successfully basically stopping from while loop with this start position incrementation for this one. So random, okay, I'm just going to assume it works because we still have to go ahead and add these points. So we have added our points. You see, we are actually not seeing them. So that's pretty bad, I think. So where's the issue could be? If not, maybe this one. If not, length of the dictionary. Uh, uh, maybe the length won't even work on this. So let me actually disable this. So are we creating new points? Nope. I think that's good. If start position is actually right. My bad. We have to do it if it's smaller. If start position, because we start with 0, is smaller than perimeter, then add, right? And that should work now. And it's my bad because I didn't actually turn this to the, since we do not have any point, this logic is not going to work. We have to actually go ahead and run over the details only one time. And it should be, let's take a look at it. We have 12 points. That seems correct. And now we have to go ahead and move this point. So let's go ahead and set point attribute after we have randomized the width. And basically we have got our random width. We just want to go ahead and add this to our start position. Actually want to set the point position to the start position. So set point attribute. So 0 name is going to be position. Point number is going to be our new PT, and the value is going to be set. Since we are using variables, we actually have to use set function to set a vector. So on x is going to be start position, and y is going to be x, y, and z. Y and z could be 0, and mode we can use this one, and basically that's it. You can see our points are now randomly created. If I use a seed, you can see that we can be pretty sure that this looks correct. This will be very nice for us to copy along the curve. This looks correct. And one more thing I want to do is go ahead and get some of the attributes from this while loop to my point, because right now we don't really have any way for us to get these points back to trace these points back to the widths and IDs of these geometries. So what I want to do is go ahead and set point attribute. So the name is going to be, let's call this width. Point number is going to be new PT. The value is going to be the random width that we just randomized, like that. And I also want to get the name of the name that we just randomized, which is basically the key, our key array, and then the index of the random function, because it's going to give us the mapping back to the internal name attribute of our piece. Just copy this. So let's call this basically I want to make sure that this is where actually this one actually went ahead and get our internal name attribute name, copy this and put it inside here like that. For the new pt, and the value is going to be our with keys random piece like that, and this should be basically it. And let's if you take a look at these points that we just created, so we have our name attribute is correctly set up, and the width of it also like that, and we go ahead and randomize. This looks very nice. So yeah, so this is logic for this, and let's actually, before we move on, let's actually go ahead and build out everything out to this network to see the actually the how the along the curve instancing is going to work out. So let's do that quickly. Let's start by creating making add node. This add node is actually go to the polygons and create by group, and it's going to basically automatically create a polyline from these points. And this polyline should be basically well set up because our points come in basically in order, and that means the polyline is not going to have a weird vertex order. After that, I have to go ahead and convert to line. So this convert line is going to basically split this polyline in individual primitives like that. And then I want to transfer the width of my points that I stored from the wrangle to the primitive attribute of this on every one of these primitives. So what you can do is attribute promote. So we want to go from original name going to be width from points to primitives, and make sure that you from the promotion method you want to first match, because every primitive is going to have 2 points, and every one of these points are going to have its own, basically it's going to have 2 widths, basically there could be 2 widths that are not correct. So let's turn off also this wrestling. So basically if you imagine, for now that we have cut our polyline into its own primitive pieces, every primitive is going to have 2 points, and for every one of these points it's going to have widths, basically the width of the first point, and then for the next geometry it's going to be completely different. And for the promotion, if you do an average, it's going to average between 2 widths, and that's not what we want. But since the vertex order is going to be ascending into this one, we can just use the first match, which should basically take the lowest vertex, or whatever it uses, basically lowest point, and use that as its value. So that should be good to go for us. And now I want to go ahead and use that path def path default node, and here connected this geometry, and then we want to long it like that, and then go to the capture. Forward direction is going to be x-axis, because we are using x-axis because our polylines along the x-axis. So you can see it looks pretty good. We just have to make sure that we have fit this polyline all the way. So go to this map length using fraction of core length like that. Like that, you can see we have distributed our points along this polyline. And now we actually want to go ahead and calculate the new parameter sizes of these new point primitives, because once you have moved them along the curve, they're going to be a little bit different than the bounding box sizes that we set inside here. So put down a measure sub. In this measure sub, I want to go ahead inside and basically measure it again. Parameter length, we can call it parameter. So we can have 2 attributes: the width, which is our original width from the dictionary, and parameter is our new parameter. You can see it's going to be a little bit different. So you can see 1.58 and 1.59. You can see there are little differences between them, and some of them are actually a lot different. Something like this 2.6 and 3.0 like that. So this is why we want to do. You see this one. There's probably a lot bigger discrepancy inside there. So yeah, so we have remeasured it, and now we want to basically set it back to the point. Set back this width. We want to basically divide it. We want to divide our parameter with our dictionary parameter width, and then set it to the first point of that primitive, because we are going to copy to because all of these attributes has to be on points and not primitives. So primitives are only, we're using primitives only because we can actually measure them. So put down a wrangle node. Next, we're going to be pretty easy code. So inside here, what we can do is create a float. Let's call this scale equals actually not, f at perimeter, which is our new parameter. I hope I wrote it correctly. Divided by f at width, like that. So now we have our scale is correctly going to be created correctly, and now I want to set this on our parameter, our scale on our point. So what I want to do is calculate, determine on which axis I should put my geometry scale, because we have option for us to use as x or z axis, and that means we have to also put the scale on either on the x or z axis. So let's do this like that. So we can probably create a new vector. So let's create a new vector, because scale can be basically a vector. Scale equals is going to be doing like this, chi. Let's go ahead and reference our size axis equals, we're going to ask a question, is it equal 0 question mark, and if it's 0, then set our scale parameter to the scale 0 1 and 1, because scale should be 1 1, and if it's not colon, then we want to set it as a, we want the z axis, so that's going to be scale is going to be 1 1 and scale, like that. So our vector should be set, so it doesn't like this one. All right, we already have scale. Let's call this scale vector, and then I want to set it on a first point on a primitive. So what I want to do is get the first point of the every primitive. So you see we are actually running our points, want to run over primitives to get these attributes. So I want to get the integer first prim pt, let's call it like that, and we can use a prim point function, which is basically returns the point. We have to give it a primitive number at primnum. And then the vertex that you want to use, and we're pretty sure that's always going to be first vertex that we want to get our prim pt. So we have pt, first pt, and then we can just set point attribute. So this is going to be scale, because this is one of the attributes going to be picked up by the copied points node. Point number is going to be prim pt, and the value is going to be scale vector, and this should be correctly set up. Let's take a look at these. Our points, we have our scale. Let's go to the z. You can see if it change z, it's also changed that one. You see the scale is pretty close to 1, but some of them are actually different, which is good. Okay, so the scale should be correctly set up now. And now what we can do is we can basically connect back this polyline, create a polypath, and in this polypath we don't even have to do anything. It's basically going to connect back to the single polyline, and this is good because we want to use our orient along curve node. So we're going to create a up and normal attribute that is used by copy to point node to actually go ahead and orientate geometry that we want to copy to point. So with these default options, let's actually go ahead and put down a copy to point. Take a look at how it looks. So copy geometry to copy. So that's now points copy to, and we can, for geometry, we can basically put anything after this for each loop. I'm just going to put point like this one. And for the piece attribute, I want to go ahead and use my CHS internal name attribute, because that attribute is that we actually set as a name of these pieces inside this wrangle. For the piece attribute, so you can see it looks pretty weird because the orientation is not correct. So this is where the oriented along the curve comes in handy. First of all, I want to make sure that I go ahead and rotate this geometry, apply yaw. I just want to move it by 90 degrees, by negative 90 degrees. You can see it still looks wrong because it doesn't point to the next geometry. This is because of the tangent type in this framing. Just go to the tangent type and go to the next edge tangent type. And if we have done this correctly, our scale should be set up correctly, and it's basically going to always be correctly orientated along the curve. We can use a pack instance also. Then we can just go ahead and try out our seed. You can see we can use a seed, whatever is going to be correctly laid out. Go move the curves around. You can see basically can do whatever we want. At the end of it, it's going to be very nicely laid out polyline. Let's implement another way that we can align our geometry along the curve. And this time I want to be able to use a noise. So let's start by creating this noise. What I want to do is go to my reference polyline and add a attribute adjust integer. Connect this up, and this is going to be generate our noise. So instead of pattern time is going to be random. We can do not random but noise, and then you can choose whatever noise you want. And I want to attribute name, let's call it noise. Now we want to control the max value. So this is where I want to go ahead and reference attribute that we created inside here, which is the max piece index. So let me copy this one, and let's create this. Let's create a spare parameter so that we can start referencing this node. So by default, you can add spare input from the menu up here, and then you can just go ahead and drag this node to the spare input parameter. You can see it's going to show this line. This means you have spare input. Or if you are using one of my tools, let me show how it's easy, how much easier it is if you're using my Houdini package. Just select this node, this, and then go to the here and add spare input. It's going to automatically create a new parameter, and it's a lot faster. So now I just want to go ahead and reference this detail attribute. So -1, and it is max piece index, like that. Now we should have value 4. That means our noise is going to come from 0 to 4, like that. And we can actually go ahead and visualize this noise. In this noise marker, you can see values. Well, it's a little small, but what's good about this, that we can go ahead and change the size of it. So this is element size, basically how big. So you can see that we want probably, if we want less values, we can increase the size of the noise. Or if we want more variables, varied copy, we can decrease the size. So we're going to better see how it's going to look once we have actually created the actual logic. So put down, let's actually copy this wrangle node, previous wrangle node, and let's connect this noise inside here. since we have a noise now, and so we can delete the seed parameter because we're not going to use a seed, because basically the seed is going to be controlled from here as an element size and offset. So we won't gonna have any seed parameter on this node. Let me just go ahead and open this up inside code. So we still want our dictionary, we still want our keys, we have our total core length, which is good. We have still our name attribute, which we also need. We still have start position, which is good. So what I want to do is change how we are actually getting this random piece. And this random piece is actually going to be used, we're going to use a prim UV attribute. So put down a prim UV. So geometry is going to be, so I want to sample it from our curve, which is going to be input number 2. Input number 2, attribute name is going to be noise. And then we have to give it a prim number. So we know that this curve has only one primitive, it's a one curve, so it's going to be primitive number, it's going to be always 0. And then we have to give it a vector on where from what we should sample our from where we want to sample our noise. So we do not have like any of the, so basically we don't have any UV attribute, but this primitive UV function is actually using the intrinsic attribute of the UV attribute of this curve. So basically we can imagine that by default, without any attributes, this curve can be laid out across 0 to 1 space at the bottom of the UV grid space. So basically we want to sample it and make sure that we don't exceed 1 from here. And the noise, basically how we're going to do that is we're going to take our start position, we're going to divide it by the total parameter. Since we are not actually, since our start position should never exceed total parameter, so that means we are never going to go over the 1. And then I just want to basically we don't have to do any of the multiplication because of the this attribute is already correctly set up. And basically it's going to take the closest one that it finds. And I think we should, let's take a look at what it says, what it doesn't like. So it has syntax error. So let me take a look. Noise prim UV. Right, we need this one. And I think it's actually, let's take a look at it. So you can see we are actually starting scattering these points. Let me go ahead and change this noise. Element size, like that. Offset. Okay. And let's put down the switch node. Let's switch between both of these and then just put it inside here, and let's take a look at the end result. And let's switch to the second one as a noise, and then let's offset our noise, element size and offset. You can see that there's more of a chance that multiple same pieces are going to be together like that. And one last way that I want to create my geometry along the curve is using a pattern. So this pattern idea I got from a chain SOP node. We go to the chain. You can see that you can actually go ahead and put our curve geometry inside the first input and the second one as our curve. If you take a look at the chain SOP and go to the alignment x-axis like that, you can see it's actually went ahead and aligned also my geometry along the curve. But the difference is that this geometry is actually not instanced, it's actually curved. You can see that even though our pieces are all flat, these are actually bended like that, and they are not instanced. You can see we have a lot of primitives like that. So yeah, but thing that I want to actually copy from this node is actually go to the chain pattern, go to the pattern, and you can actually create an explicit pattern. And this explicit pattern is going to basically give us option to select attribute, and based on that attribute create a pattern. So by default, since we have not given any attribute, and find pieces are by connectivity, and connectivity is going to be generated by the integer attribute. So that's why it's actually this drop down menu is all integers like that. So you can see if I select 0 and 1, and it's the first piece, and second one is repeated along the curve like that. So I want to implement something like this inside my tool also. And there's also custom, and what's interesting for me is also custom implementation of this drop down menu. So by default, these are actually these would actually replace each other. Basically, if I select something new, it would actually replace the entire string, but you can see it's not replacing, it's actually appending to it and creating basically a new string. And that's why actually if you take we can actually get our main code for this pattern, for this drop down menu from the what is called class pattern like that, this parameter. And if you take a look at it under the menu, it's a Python code, and this is the way that we are actually that this tool is actually generating this menu, and also it's also implements the custom implementation of this appending to the already existing string. So what we can do is basically get this code and modify it a bit to be used of in our tool, because we are doing a little bit differently this setup. So yeah, I have written out this code. I'm going to walk through it while we're doing the things we do. And yeah, so let's start writing it out. So let's go to our fence tool, type properties, and create our new string parameter. Let's call this a pattern. And in this pattern, go to the menu, use menu script, and this is in chain swap. It's a replace field plus single flag menu. So we want to also make sure that we have the same one. So we want to go ahead and copy some of these parameters so that I can just talk you through this, what we're doing. So we are getting a node from our Quark dictionary. So in this menu script, we have Quark dictionary, and it's basically we have a node that this drop-down menu was called from, which in this case would be always be our HDA node, and also the parameter, which is our Quark's parameter, parm. So basically this pattern parameter reference this one. Then we want to, and so what we want to get more is our attribute node. Attribute node is going to be basically node within our node. So you see we have node, and node.node is our curve geometry, which I went ahead and renamed this last triangle node where we did our pre-processing of the geometry. I went ahead and named it curve geometry because we need some meaningful name for this node, because we end up referencing it outside this network. So I just called it the curve geometry. So this is where we're actually going to get our attributes from, attribute values. And then I want to get the internal name attribute, which is the parameter on this HDA, which is our node parameter internal name attribute. And then since we are not using the parameter object, we just want to get its value, which is eval as string. So now we want to go ahead and create an empty geometry list. So this is what we're going to return. And geometry, we want to check if this attribute node has a geometry. So there are cases if we have not basically connected any geometry to this HDA, that means there's no geometry, and we do not want to try to generate. Basically, we don't want to further try to generate any menu items. And for the logic of the menu, let me paste this in. Let me apply it. Now let's take a look at this, how it should theoretically work. It should work the same way the chain swap works. So if I go ahead and select my value, like something like a safety rail value 1, and if I select maybe like a 2, you can see it didn't replace it, even though our menu is replace field. So basically it doesn't look like it actually replaces it because of its value set. It actually basically for every one of these menu, its value is already set as this string, which is already in a pattern, in a parameter, plus these values. So this is the reason why it looks like it's not replacing it, even though internally it's actually replacing entire field. So let me actually show how it works. So what we'll do is create our list menu. So Houdini expects that we return an even number of elements, our element number of strings of this menu. So this is going to work as a string, as a parameter, as a drop-down menu value and a label. Much like parameters have a labels, and it has a names of it. So name that we reference in any of the parameters, and label is just a human readable label. So let me actually show how it's actually going to work. So Houdini expects us to return a list. So let's assume our list is only out of 2 menu items. So that means we have only 1, 2, 3, 4 values inside this list that we are going to return, and every 2 of them, so every pair is one single menu item. And so the one index 1 for every one of these pairs is going to be its value, and the second one is going to be its label. So that's why I want to make sure that we generate this menu as its first value is going to be already a value that is inside this parameter plus this menu item that we can select. So we get our attribute values, and for every attribute value we are getting the current pattern, which is our eval as string this parameter. So in this case our current pattern would be this one. So basically if it's not empty, we are joining our current pattern with the attribute value that we got. Basically every attribute value that we want to show as a menu item, we just append to the menu, and then we also want to get our label. And for the label, it's always going to be just the attribute value, so that we do not have like a huge strings as its value. So here we just know that we just want to add this one, it's going to add it to it. And then we just return this menu, and that's it. And this is basically the same implementation that we got from the chain swap. So this is just for the menu. Let's actually go ahead and implement inside the VEX code. Let's start by putting down a wrangle node. So let's connect the same way we have connected both two previous ones. So the width dictionary is going to be number 1, and the curve is going to be number 2. Let's open this up. So in there's a little bit different setup for this. So we have our pattern. So let's get our pattern. Let's call this, it's going to be pattern CHS. So we called it pattern, the parameter. So this is going to be a raw string of this pattern. So what we'll do is go ahead and convert it to a string array. Let's call this pattern array. It's going to be split. We're going to split our pattern with separator of white space. So it is important that all of our name attributes actually do not have within their attribute values do not have any white spaces, because it is a separator that we are actually using to separate different attribute values. So it is important to know that. Yeah. So make sure that you don't have any white spaces in actual attribute values. Now I want to get a total parameter. So let me actually go ahead and copy this from here. Our curve total parameter. We also want to get our name attribute, internal name attribute. So let's copy also this one. From here, internal name attribute, also get our width dictionary. So we have also, let's copy it, paste inside here. Okay, so now we want to go ahead and let's check our width dictionary. So you can see that in previous one we actually checked if our length of our width dictionary is more than if it's not 0. So let's actually use the same check for the continuation of this one, because if we do not have any bit dictionary, anything after that is just going to basically hang Houdini. So what we'll do is go ahead the same one as the float, start position, equals 0. And now what I want to do is while loop, basically the same while loop as inside here. While total parameter, let me do that. So inside here, let's actually go ahead and disable this node so we do not trigger this while infinitely. So in this while, what I want to do is create a new point, just like previously. Int new pt is add point. So it can be 0 and point number is going to be 0, 0, 0, like that. Now I want to get my right, this is a little bit different because we want to put this new point creation inside our pattern array. So what we want to do is we want to keep looping through this pattern array as long as our start position is not as long as our start position is smaller than our total parameter, just like in previous ones. So let's actually do it for each. So it's going to be, let's call this string pattern piece. And array is going to be our pattern array, like that. So we're going to keep looping through this and add new points through this array. So in this, we create a new point. Then we want to get our width of this point, of this pattern point. So float. Let's call this piece width. Is going to be our width dictionary, and it's going to be our pattern piece. Because our keys should be the name attribute. Our keys are the value of the name attribute. So it should get our piece width. And then what we'll do is go ahead and start setting this point position. Set point attribute. The name is going to be position. Point number is going to be new PT. And value is going to be start position. Start position like that. Then we want to go ahead and increase our start position. Start position plus equals width, piece width. Like that. And then we want to set our attributes. Set point attribute. The name is going to be our, so this is the one that we are hard coding, which is a width. And piece, so the new PT, and the value is going to be piece width, like that. And then we want to set our also the name attribute. Set point attribute. Let's just copy this. And in here we want to, instead of width, we want to get our name attribute. And the name is going to be the pattern piece name attribute, like that. And let's enable this node. And if you take a look at it, we should be, and also make sure that we are doing it one time over point. Details like that. You can see our pattern looks something like this. So let's go ahead and connect this to the switch, and let's go back to and if we have set up our attributes correctly, let's go to our copy to points. So you can see our pattern is complete. And let's say we want to change our pattern, so let's actually clear this out. And so we see we are actually triggering it. We are now triggering it. So let's actually escape. Make sure that let's actually make sure that we do not infinitely load this if we have if this pattern is actually empty. So what we can do is so the length of the Vic dictionary is not empty, which is good, but it doesn't account. So if this basically we know that this Vic dictionary is not empty, but what is empty is our parameters. So that means we have to make sure that that is also not empty when we want to, if we want to create this pattern. So what we can do is just copy if this is not, and then we can just put end and the length of the pattern array. And if the length of the pattern array is also not 0, then we continue. So let's enable it. Let's take a look at the end of it. So you can see we are not hanging Houdini, but if you, let's say, select one of these, we should be creating this pattern. You see, this is the pattern 0. So if we disable something like this, it should probably, we should also accommodate that it's something that is not valid. You see, it's now tries to find it. So you probably want to also make sure that we can. So we shouldn't really do it manually. We shouldn't select any pieces manually, but we should probably in our code accommodate option that this pattern is not valid. So let me do that a little bit later, but let's just see how it, if it's correctly set up. So let's say I select my pattern piece 1 and 2. You can see we are now instantiating this geometry 1 and 2 times, like that. So yeah, so this is pattern is pretty much done. And let me just take a look how we can fix this infinite loop if it's not a valid pattern, and then we can just move on. And one way we can, and thing that it actually keeps freezing our Houdini is that we are giving an incorrect key. So what we can do is once we are looping and we are basically trying to first time access this piece with, what we can do is go ahead and check it. If is valid index, and what we have to give it our with dictionary, and the key is going to be the key that we are running over, which is the pattern piece. Basically, if this is a valid, basically if it's, what we can do is if it's not 0, basically we have to encapsulate everything inside. After that, all the setup inside here. So basically we're checking if these keys actually exist, and then we can continue. If it's not, then don't. So let's actually go ahead and try it out. So it should work the same, but let's say I have went ahead and deleted some of these. You can see it's actually it doesn't like, because of it's basically going to try to go to the our pattern looks a little weird because we are actually go ahead and creating points, lots of points at the beginning of this one. So what we can probably do is not create a new point. What we can do is create a point inside this here, like that. And I think this actually solve it. You can see, right? So you can see that this is not valid. So this means that we are basically looping over this piece, and this piece is never going to be captured. It's only going to choose first one, because this is the key that it actually can find. So yeah, so for now, yeah, so we have successfully created so that it doesn't freeze Houdini. So that's good. So this is basically done with our different patterns. And now let's implement some of the Python logic in this HDA. First, I want to actually populate this multi-parameter with these initialized pieces that we set up at the beginning of the tutorial. So what I want to do is basically fetch the piece, basically fetch the internal ID attribute name. No, actually internal name attribute name, and set this label parameter as its name, so I know which piece I am actually changing width of. So I want to definitely implement that. So yeah, let's start with that. So what we'll do is go ahead and go to top properties, and in this code I want to create a Python function which is going to be inside scripts. In the scripts you can go ahead and create a Python module, custom script, Python module, and apply it. And basically here we can write our functions that we can call from callback scripts or from really anywhere inside Houdini. So I'm going to call this def let's call this something like def init multiparm pieces, like that. And let's give our Quarks dictionary. So I want to get my HDA node, which is going to be called node Quarks node, and I also want to get my multi-parameter counter node, which basically is this folder. So the multi-parameter consists of this pieces attribute parameter, which inside parameter is actually as a folder. This folder holds an integer value that we can set, that's going to control how many multi-parameters we have. So we want to reference basically this parameter, this folder. So go to the scripts. Let's call this multi param equals node dot parm pieces, like that. Then I want to get the node that I'm going to fetch the attribute, the dictionary from. So what I want to get this dictionary that we set is inside here. So I want to get this dictionary, so I need reference this node. So what I do is copy this. Let's call this dictionary node equals node dot node, and then this node. And I also want to get this node geometry. So this is just a node. I also want to check if this curve geometry node actually holds geometry. Let's call it geo. Let's call this dictionary node dot geometry. So I'm going to check it, and if geo, if this holds geometry, I want to go ahead and fetch this with dictionary. Let's call this with geo. I'm going to call this with geo with dictionary object. So this is going to be just an object of this attribute, which is basically just a geo dot find global attribute. And it's going to be our, since our with dictionary is static, so static name, we can just hard code it with dict, like that. So we have found it, and if we have basically, so this can there is a possibility that this attribute is not created. So if it's something has gone wrong, and basically if this is not true, if this is basically if only if it returns the dictionary object, then we want to only continue. And then we want to actually get the actual dictionary. So this I'm going to call this a with dictionary equals with dictionary object dot, we have to call a dicts function, and this function is going to return a list of all the dictionaries, basically all the unique dictionary that this attribute holds, and it's going to be a list. And we know that we have only one unique dictionary in this attribute, so that means we can always just simply call 0, because we could find dictionaries that are actually like a point or primitive attribute, and that would mean that there are many dictionaries. So if you take a look at actual documentation on the dict function, you can see that it returns a dictionary table of this attribute. So basically, if our dictionary attribute would have been like a primitive, we have a lot of primitives, but this would not actually mean that this dictionary would be copied on every one of these points. It would basically store integer index of that. So basically Houdini would store every unique dictionary inside like a table, and it would only assign like an index to that dictionary for every primitive to look up this dictionary. So that means this is why actually it just returns a dictionary list. And since we have, this is a detail attribute and there's only going to be one dictionary, we can just call a 0 index on it. What we want to do is set this multi-parameter piece to the amount of the length of this dictionary. So what we can do is multi-param dot set. I just want to use the length of this with dictionary. We can just close it, apply it, and let's call this function on this button. So I just copy the name of this. Actually, let's copy also this entire signature like that. Go to parameters, initialize pieces, and this callback script who.phm. PHM is basically a shortcut function for getting the Python module. So basically getting this Python module on HCA, and just call this function like that. Apply it. So let's press it. You can see if I clear this out, I initialize pieces, you can see it's going to do to the 5, which is good because we have 5 unique pieces and this looks correct. And now only thing I want to do is set this label correctly. So let's do this. Let's go back to script, and what I want to do is I just want to go ahead and loop through this dictionary. And for the dictionary I also want to get the index that I am looping over, because every one of these multi-parameters are basically suffixed with its own index. So what we can do is actually enumerate. Let's call this nom, and let's call this name, because dictionary in Python returns, if you loop over it, it returns a key, if I remember it correctly. Let's enumerate. It's going to give me, okay, this won't give me a completion, but basically we want to enumerate our dictionary with dictionary like that. So in this for each loop, what we can do is get this name parameter. Let's call this name parameter. So node dot parm, and then we want to do an f. F is going to basically want to we're going to format this string. So we know that our width offset starts right now. Actually, not width offset, but piece name attribute is basically piece name. So what we can do is go ahead and copy this name. Go to the back to scripts. So we need piece name, and then we want to go ahead and insert our index for every one of these, like that. And this should be probably, so we have gotten our parameter like that. Let's actually, if you're getting, let's actually go ahead and print it out. If you're getting our name param like that, let's print it out. Let's take a look at it. Okay, so you see, clear it out, you can see we're getting these parameters, every one of these. So that's good. So only thing I want to do is go ahead and set it. So I'm going to assume that we have gotten it, because we have in the same code we have already set this multi-parameter, so we do not have to check this for validity. So we can basically set it to the set it to the name that we are looping over. Dot set name like that. Applied. Let's check it out. Initialize. So you can see piece name. It can fetch the name and set it on all of them like that. Yeah. So what else we can do? So we could probably also get the size of since we're looping over it, we can probably also get the size of these pieces. So what I can do is go ahead and let's go to the parameters and let's copy it, piece name, and let's call piece width, and just return the to piece width. Let's just copy it, apply it, and let's get also our piece width. So what you can do is go ahead and let's get the width in its own variable. Width is equals, well, actually no, let's do this in one line. So what we can do is Let's call this width param equals node dot param. So we're going to, what did you call it? Piece width. Let me just copy it. Piece width. Make sure that you also format it. Also num, like that. And after this, you want to go ahead and set it as our so since we are looking over the dictionary key, we want to get our width dictionary and then get the key that we are looping over, which is a name, like that. And this should probably be everything we need to do. So let's try it out. Oh, actually, yeah. So this is actually this string. So it's actually complains that this cannot string a parameter to a float. So what we have to do is convert this dictionary value that we get is actually a string. So convert it to a float. So let's try this, clear this out. Let's try it again. Cannot set the string param to a float. Oh, it's actually another way around. This actually piece parameter actually expects us to give it a string, and our dictionary is actually a float. So what you can do is go ahead and convert it to a string. I think we can do this like that. So let's try to get it again. Okay, so now we have our widths. But you can see these are very big numbers. Basically, the precision is way too big for us to have a meaningful read on it. So you can do basically slice this string that we get. So after we have gotten our string, once we have converted it as a string, we can just put it in a square bracket, 0 and colon, and let's say 1 to 6 only values for this string. Applied, so we have sliced our string, initialized pieces, you can see now only 6 values. So it's also going to, dot is also going to be part of it, but this is something that we can work with. These are not that huge of a numbers. So we can now see the width piece width. So let's rename it piece width. Something like this. Let's actually try to maybe horizontally join with the next parameter, how it looks. Okay, so it looks actually pretty good if you do not have a super long name, piece name. So yeah, I'm actually pretty happy with this one. So these are pretty big because of the Unreal way of naming things, but if you have like custom geometry, the name should probably be a little bit shorter than these crazy names. So yeah, and I'm pretty sure that if we would rename our geometry inside Unreal Engine, it would basically also basically if it's in content browser would be like a shorter name. It would also, and if we imported it inside Houdini, it would actually be also a short name. So yeah, so that's just the thing that we have to kind of live with. And now let's implement our piece attribute selection. So I just want this similar to this, basically just a drop down menu. So let's implement it. So in this, in parameters, go to the piece attribute and go to the menu and use menu and replace field single selection menu and apply. So you have to be careful right now because right now we are not actually fail checking if this attribute doesn't exist or is empty. So if, let's say I put it on a, let's say this is now empty, our for each loop is actually going to run through every primitive because it references this parameter. So what I want to do is make sure that I actually go ahead and maybe put it on single pass. So once it's empty, it doesn't try to loop through every piece. So yeah, so this is just for the fail safe. So what I'm going to do is go ahead and create this menu script. And it's actually pretty simple. What I want to do is get my input geometry. So I have this null node. Just going to copy this node and let's reference this node. Let's call this input geo equals. So let's start by getting this node equals quarks node. So input geo is going to be geo dot actually node dot node input geo, like that. So after the input, what to do is check if this has any geometry. Geo equals input geo dot geometry. If geo, we want to generate our attribute menu, and it's very simple because there's actually a special function for it. And let me open this up. So under the geometry class inside Python, we have a generate attribute menu. We just want to go ahead and copy this generate attribute menu and put it on the side. Geo dot generate attribute menu, and we just have to give it a couple of types. So we have to give it the attribute type that you want to fetch, which is who.attrib type. And if you open this up, it's basically who.attrib type dot point prim vertex global, and you know it's a primitive. So just paste it as a primitive, and then we have to give it also attribute data type, and which is going to be our string. So if you open up this one, it's going to be who.attrib data. We just have to go ahead who.attrib data dot string, paste inside here, and that basically it have generated our menu, and we can basically return it. So, and if there's no geometry, you want to return an empty list, like that, and then just apply it. Let's take a look at our menu. So this should now have everything inside here. So, and to make sure that we do not write a piece attribute that's not valid, we can probably put this to the I think it's like a toggle, maybe. Actually, I guess it's a normal then. And this menu should look something like this. We can basically select our attribute. This one to use as a piece attribute. And what's good about all this setup, once we are, let's say we select Unreal Material, we press initialize pieces, you can see it's, well, it uses the name of the material, and we know that it's, well, it's just a one piece, so it's basically going to, we know it's incorrect, but all of this naming and width is actually set up properly based on the attribute that we input. So we can put any of these attributes and it's going to check its name. So this is incorrect fbx, so because it's a source file, it's .fbx, so it's cut off everything else. So but if we know that we have our input mesh like that in its pieces, it should look correctly. So this is good because we have set up our loops like that, so that it's kind of a universally going to fetch information. And one thing that I want to also implement is to kind of safeguard me from too many iterations. So what we can do is actually put this max iteration when on specifies maximum number of iterations that are allowed. So what I want to do is give it a hard limit on how many pieces that we can connect to this HDA, because there may be options, there may be a case where basically we are starting to loop over every piece of the primitive because we are running our primitives. Let's say there's option that there is a case that this is actually empty, and when this is empty, it's actually going to start loop through every primitive, which can take quite a bit of time if we have lots of geometry. So what I can do is basically put a max iteration, something like 50. So that means it's going to loop through 50 times. If there are less than 50 pieces of geometry that we are actually connecting, that's fine. But 50 is kind of a hard limit for these. And we can even maybe promote this as a variable to our HDA too. And now with the main logic complete, I want to open this HDA inside Houdini session sync with the Houdini engine. So go ahead and open Houdini session sync. Just make sure that you save the previous work that we did up until now. And now what we can do is open this up. And right, now let's go back to Unreal. And what I want to do is go ahead and drop this HDA. And if we have our Houdini session sync, it should basically load this HDA inside here. So between the videos, what I did is let's allow editing of content. So what I did is go to the type properties, I changed the names of the input and output, basically curve input and static meshes for our HDA input. And another thing that I did is actually went ahead, go to the parameters and go to the pattern. And this pattern actually gave me, I tested out for the bug fixes and actually gave me errors when I tried to load it via Houdini session sync, because of this problem of us actually not checking if the attribute actually exists. Basically, in these attribute values, we basically right away went ahead, go to geo.prim string attribute values, and then we just pointed to the internal name attribute. So when we are loading this HDA inside Houdini through the session sync, these attributes are basically not visible to this parameter, and it basically throws a error. So what I want to do is make sure that I actually find this attribute. So if I geo.find prim attribute and then just point it to the internal name attribute, and if we have found it, then only then continue like that, and then this we won't have any error messages. So make sure to do that. You can just go ahead and open up this HDA and take a look at it, at the code, so it's always available for you. So another thing that I did is set up my inputs. So static meshes, I unfroze the geometry, and make sure you do not delete this node, because we're actually referencing this inside our parameter. I think we are referencing this node inside the piece attribute menu. You see we are getting input geometry, and this is input geometry, input geo. So make sure you just unfreeze it and do not delete it, because we need our input geometry for the menus to work. And then the curve, so we still have our resample. We're going to work a little bit on how on different ways that we can create this curve, but for now we can just put down a resample from the input curve. So you can see by default it's the curve that is given by the Unreal Engine. Let's actually go to the Unreal Engine and make this curve a little bit bigger. So go inside HDA. What you can do is go to the input, Houdini input, and go to the input curve. And what you can do is just drag this curve out. And then you can press an Alt. It's going to basically create another curve point like that. And if you do not see for the input curve input as a curve, you just go ahead and change it to this one. So basically we want to curve input on the first input, and another one is want to geometry input. That's going to be our static meshes. You can see it's an empty curve because, well, we have no geometry. But what's cool about this Houdini session sync is that if I go back to my Houdini, you can see this curve is actually imported. You can see it's I can actually put down a null node, and let's call this like input curve. You can see we're getting the raw curve that comes from the Houdini, from the Unreal Engine. And if you're getting these two curves, that means you are basically this visibility ghost other objects is turned on. So make sure you can just hide other objects like that to see the only one curve. So basically this is our raw curve, and then we are resampling it to make it a smooth one. So we're going to control it a little bit later, because we could make it some like straight edges like that, and then we could like treat them as a different pieces of geometry. So that's going to be a little bit later, but for now let's keep it as a sample. And this sample is pretty big, so we can make it maybe like the little lower resolution. So but everything inside here should work just fine. And make sure that after the copy to point, you're putting the output node, because you want to output this to the Houdini. And for the options of the way that we are actually going to select the option to scatter it, what I did is went to the created the menu. So let me just go to here. So what I have is a drop down menu for distribution type, random, noise, and pattern, and then I have just folders with these parameters. So random, noise, pattern, and it's going to basically disable it, whichever basically disable other two, whichever we have selected. So for the random, I want my seed parameter. So let me go through. So this is my random. In this random variable, we have the seed. So this is this parameter. For the noise, I have no parameters on my variable, but I have all the parameters on this attribute adjust integer, element size, and offset. So these are these two. And for the pattern, I have my pattern is going to be, so the pattern we already created and just put in the subfolder of the pattern. So yeah, so these are all the options that I want. So that looks good. And with all the options inside here, I can go to my Unreal Engine, go this way, and let's say I want to make it by, so instead of pattern, I want to make it by random. That's fine. You can see that some of these parameters are not actually hidden when we are inside Houdini Unreal Engine. You can see even though we have like a hide when this is a, let's say, random, noise and pattern in Houdini would be hidden, but in Unreal Engine it's not showing as hidden, so that's a little annoying. But once we have randomized, we can put out seed. Obviously we're not getting anything because our core, we have no static meshes. So go to the static meshes you want to scatter and just drop this 4 inside here, let it recook, and you can see we are scattering this jump. And now I want to also, for me to have ability to actually handle these straight lines. So let's say I do not want to this curved, this kind of a organic line. I just want to the same ones that are in this HDA, which is basically just a polylines like that. So I want to create my fencing with the straight edges. What you can do is go back to the Houdini and handle the curves that are incoming from it. So right now, this is actual Houdini curve coming in from the Unreal Engine. So what I want to do is give this resample option for me to treat polygons as straight edges. So basically I just want to go ahead and promote this as a variable. So let's assume I have done that, and make sure that you also resample by polygon edge to make sure that at the edges there are a polygon like that. So if you have Houdini session sync, this should already be updated inside Unreal. So let's take a look at them. So you can see some of them look okay, but some of them actually are not, because it's still being treated as a single polyline, and the chances that are we have randomly selected precisely the sizes of these pieces so that it hits the corner is pretty small chances. So that's why it's like that. So what I want to do is actually go ahead and separate this. I actually just want to cut this polyline in its own polyline inside its own separate pieces like that, and then basically run through this logic for every one of these cut pieces of polyline. So what I want to do is go ahead and remove inline point. So this is basically going to work only if we have our straight edges. So if, let's say we have this one, we have our straight edges, and since we are resampling, in every case, whether we want to straight or subdivision curves, we're going to still be resampling it. And since I want to cut it, I want to just remove the points, all the points that are in line, and put them a convert line node. In this convert line, we can disable rest length. We don't need that, and this will give us our polylines for it. So this is going to set. Now we have 4 primitives like that. Then I just want to go ahead and create a switch node. Switch if. Another thing I want to here to switch whether we are using a straight lines or subdivision curves. So just copy this and this switch if like that. So let's say I want to straight edges. This is going to be number 1, and subdivision curves. Actually want to invert it, which is you can just basically do it like that without any needing of the logic like that. Straight edges and subdivision curves, like that. And now I want to just put down a for each primitive loop. For each primitive. At this measure stop, I want to put it inside here, I think. So this looks kind of weird right now, but let's clear this out. So the input is going to be our switch node, like that. And then for each one of these primitives, we are going to run through this logic that we set up, like that. So let's take a look at the end of it. So for the primitives that have basically, for subdivision curves, it looks basically the same because we have only one primitive. But let's say we have selected the straight edges. You can see since we are running through this logic for every primitive, we are getting these straight lines like that. Let's actually go ahead and log them at the engine. You can see we're getting these straight lines, and we can just take a look and drag these out. Okay, so now we have our straight lines. The tool works just fine, but there is one issue that I want to fix, and this is the geometry that it actually generates. So if you take a look at this instance static mesh components, and if you go to the static mesh, you can see that it's actually referencing geometry that comes from this HDA. And this is not what I want. I actually want to reference the geometry that I have already downloaded from Megascans, because this Megascans is properly set up for Unreal Engine. We don't have to worry about the loads and anything. And this geometry is not always ideal. That comes from the HDA, and also the naming is pretty bad. So I want to make sure that I actually instantiate this geometry and do not instantiate geometry that comes from the HDA. And this is done really simply by setting up a Unreal instance attribute on our points that we generate from HDA. So let's go to the Houdini. So inside this Houdini, we are not going to use this copy to points node at all. So this copy to points node is picked up by Houdini engine, and it knows that it has to instantiate geometry that it copies to. So just like in here, we have once we have copied, we have this. We can see this geometry, even though on the points we don't have any attributes that actually points to this geometry. It just knows that it's instantiation points, and it basically knows it. I think it's kind of like intrinsic attributes on these points. So, but we are not going to use these. What we're going to use just a raw point that we get from orient along the course. Just connect this to the for each end loop like that, and put down a wrangle node. In this wrangle node, we want to reference our geometry from here. So I'm just going to use my tool, my one script. I'm going to select this curve geometry. I just want to go ahead and reference it. Object merge selected, so that I don't have long lines coming from the top of the network, and connect it to the second input. So I want to go to the points. So what I want to do is get the, so for the, if we are putting it from the Unreal, so if we are referencing geometry from Unreal Engine, this attribute is always going to be the same name, which is already the attribute that we used, Unreal input mesh name, which basically is a path inside Unreal project where this mesh is located. And this is the basically in this we have to set this value as an Unreal instance attribute value on our points for the Unreal to pick the geometry not from HDA but from Unreal project. So what I want to do, so I have already opened this up. I want to get my internal name attribute. So the idea is that right now we do not have basically direct pointing to those instance to the corresponding instance attribute on our geometry, because after our copied points we are only getting the name attribute. So yeah, we're getting only the name attribute, and in this core geometry we have a name attribute, which is this one. So what we can do is, so we could have basically bring the attribute in these wrangles, bring along the instance attribute, I think. But it's not too bad if we have not brought that attribute along, because we still have a corresponding attribute which is called the internal name attribute. So on these points we have an internal name attribute, and also in this core geometry we also have the same attribute, internal name attribute. So this is going to be our matching attribute. So I'm going to start by getting this attribute, string internal name attribute equals chs dot slash. So we have internal attribute. Now I want to get that attribute value. Let's call this name value equals point geometry 0 attribute name is internal name attribute, and add pt num, like that. So now we have our attribute value, basically this one, and we want to find the first primitive that has the same name attribute value on a primitive as on our point that we are iterating over, and there is an actually function for it. So it's going to be return a first instance of that primitive, which is called, I'm just going to call this instance equals find attrib val. So geometry is going to be 1, attribute class is going to be prim, attribute name is going to be so now we have to point it to our internal name attribute, because we also have an internal name attribute on our geometry, and the value is going to be name val. So this should return the first primitive that has exactly the same value on this internal name attribute on primitive as on our point. And then all I have to do is get the that primitive's Unreal input mesh name attribute value. Let's call this string. Let's call this mesh name. Let's call this Unreal instance equals prim -1 attribute name is going to be Unreal input mesh name, and primitive number is going to be this instance number, like that. And then all I have to do is set this as my string attribute, as at Unreal instance equals Unreal instance, like that. And now let's take a look at our wrangle points. So let's find this. Now it's empty, so I probably somewhere screwed up. Unreal input mesh name instance. Oh, not -1, but so I want to string 1, like that. Let's go here. You see we have now our primitive Unreal instance attribute, and this should be enough for me to pick the geometry from Unreal. And we're back. So I'm recording this around a week later after my last after the previous clip, because of some of the issues that I ran in. So I just went ahead and updated this network, added some new features, and overall I basically, if I'm going to show everything, if I would have showed everything that I have done in this network, this video would be way too long, and the rest of it is kind of like pretty simple steps for improving this network. So I just want to go ahead and walk through the improvements and some of the more fixes that I did. So first fix was actually this noise. So in previous video, I made my noise actually within this block, which is actually not a great idea. It is because of the inside here. We are basically, let's say we have selected our straight edges, and if you have straight edges, we have only 2 points, and these 2 points are actually going inside for each loop. That means if we put noise on this one, on the polyline that has only 2 edges, that means that basically it's going to sample the nearest one for the piece to pick. Doesn't mean that there wouldn't be much of a randomization. It would basically just would sample from 2 points a possible piece to instantiate along the curve. So this is why we are not using noise that is comes from here. This is basically what I want to do. Go ahead and resample it from here, resample, and put a noise outside the network and sample it inside my attribute triangle inside here. So this still has a downside because of the at least with this implementation, because we are always sampling. So basically I took this noise and connected to the last input of the wrangle, and this would basically mean that we are always sampling from the first primitive. So when we have one single polyline, which is a subdivision curve, that's fine because this whole polyline is a one primitive. But if we have actually went ahead and but if we have a subdivision curves, so this is the one primitive, that's just fine. But that means basically for every one of these, for every loop that it comes, it will basically sample from the same polycurve line. So this means that it wouldn't really be very noticeable, but that's one thing to know, that it basically wants to sample from the same polycurve. So it's if you're starting to see some maybe weird repeating on the curves, we probably can go ahead and change the resolution of this curve so that there's just more points to sample from the noise of. But in my experience, I didn't really see anything that would actually I mean, the noise looks fine to me, because the noise basically, there's kind of like a clumping of the objects, of the similar objects. So like here, like if I put it on a noise right now, like now it is actually on noise. If you take a look at, you can see that there's kind of similar objects are in the same objects are in the same places. So I think that's fine. The noise implementation right now, it's not ideal, but it's going to, for now, it's just going to work out. Another update was made for the pattern. So the pattern, playing around with the pattern creation, is actually it's kind of, you have to implement a little bit more safeguards to make sure that this while loop never enters basically infinite loops. And the problem was that, let's say I have added a new geometry, and the problem was that basically this parameter was not empty when new geometry was added, and new geometry was completely different from these patterns. So basically inside here there were no valid patterns from our new geometry that was put inside the HVA. So that means that it would go ahead and try to find this geometry in this while loop basically forever, basically a crash Houdini. So the fix is pretty simple. Inside here we still get our pattern array, which is our pattern, which is this one, basically our pattern array that we want to create. We get it, and now we just renamed it as a row, and then I just loop through this pattern array and check if this pattern is inside our pattern, our with dictionary keys, which is keys of with dictionary. And if it is, I just want to add it to my new array, and that's it. Just loop. Then and after this, I only use this pattern array. Basically everything that basically inside here, I know that all the pieces are actually on my geometry attributes. So yeah, it's like kind of fixed too, and after that I didn't really have any issues with this, so that's good. Like that. So this was kind of quick fix for the pattern. Now let's go to, so everything inside here is basically the same. Another thing that I wanted to implement is ability to me randomly pitch, yaw, and roll this geometry that I instantiate. So what I did is, in this orient along the curve, there's actually additional rotations ability to apply it. So basically we have partial, apply roll, apply yaw, and pitch. And this pitch control is controlled by this increment pitch. But this pitch is also controlled by the attribute, basically how much you want to pitch roll by the attribute. And the attribute is actually set on top of it inside here. So I have a seed. So let me just change the seed. You can see I change my seed on my attribute parameter. You can see it changes. And you can see it actually goes up basically on both directions. This pitch. Some of them goes left and right. And I think this would actually, if I would go ahead and change my pitch to be from 0 to 1, that would actually make it so you see if my random pitch would be basically only on the positive axis, because of the random function gives out only between 0 and 1. And if I start to change the pitch amount, you see it basically goes only on the one direction. So this is why we use the fit function, and fit function is just fit 0, 1 means that value between 0 and 1 will be fit to the new value between 0, negative 1 and 1. So this will make sure that my pitch, yaw, and roll are always going to be on both directions when I randomly want to do that. So yeah, so this is, we just create the attribute, random attribute for every one of these, and then reference them inside here, additional rotations. After this, I also wanted to implement making sure that my y direction, which is basically how the geometry points upwards, always points directly to the y-axis. So this is kind of interesting, because let me go ahead and open this instantiate geometry. So like see right now I have actually turned this option off, ignore curve up vector, because let's say I disable it. This geometry likes to be the up vector is basically aligned with these with the tangent of the curve, which basically upwards like that. So if we just override it, the geometry is always going to be pointing upwards, which is good if you want to put something like a fences that are not on the you want to put fences that are not on the level ground, where you have to move around your curve a bit on the y-axis. So yeah, so this is definitely a very useful option to have on this curve tool. And then I also wanted to implement the deletion of the random points. So this is very useful. Just the lab's random selection node. There's a ratio to delete and random and seed. That's one to random. This is definitely good. This allows us to, if you do not want to like all that many geometries, just go ahead and delete them. Another thing that I wanted to implement is actually fetching geometry actually from Houdini and not from static meshes references from the second input. So how it's set up, it's pretty simple. So let's go back to the app of the network. So what I did is inside this HDA, just went ahead and created a couple of boards. So just use the edge damage node, just quickly some geometry to instantiate, something like this. So we have something like here. Let me show my grid like that, and I have added my ID attribute, which is 0 and 2, and these are actually string attributes, because remember that piece attribute for this HDA has to be a string attribute. So I can basically just inside Houdini geometry source, instead of Unreal project, I can use a Houdini project Houdini geometry source. And after that, all of these should basically update with the geometry on these geometry attributes and ID like that. And it should basically work the same. And at the end of it, we should have something like this. So we can't use this one because we have no because the geometry we have no input mesh name because these meshes doesn't exist on Houdini on Unreal Engine. But these we can copy and instantiate it, and once we have instantiated, we can go ahead and output them. If you go to the Unreal Engine, you can see they are basically the same geometry, only without material. So to add material, what we can do is either we already have referenced material as a Unreal material primitive attribute on all of these geometry that we have inside here, but if we have not, then we can basically override them. So you can see that in Houdini geometry, there's an option for me to use an existing attribute, which that means that this geometry has to be Unreal material has to be an attribute already on this geometry that we instantiate. But since we have not them, what we can do is create an Unreal material attribute. Inside here, we can just go ahead and point it to the material. So this is just and this material is updated inside here. If you take a look at it, the VX code is very simple. We check our Unreal material. This is parameter. Check if we want to override it. And if we want to override it, we check the Unreal material override name and then apply it. Let's actually go ahead and test it out. I went ahead and surfaces. I have this board material like this, so which is not ideal, but we can go ahead and copy the reference of this path and then just paste it inside here as an override like that. And this should already work. If you take a look at the Unreal, and you can see it has already applied this material, but you can see the UVs look incorrect. So I probably can go ahead and UV transform, and I can just rotate them like that. Unfreeze them, and freeze it again. And this should already update my UVs like that. So you can see we have applied the material by assigning this, so this one. So obviously they are not perfect, but for demonstration's sake, this is how we would get geometry from Houdini to the Unreal if we are not referencing the static meshes. Another thing that I wanted to implement is the ability to randomly rotate geometry around its axis. So in implementation looks something like this. So I have my ability to random piece facing. So if I turn this off, you can see that every piece is actually facing the same direction. And this is not great if you want to make it more random and not obviously copied geometry. So let me go ahead and turn this on. You can see now it's randomly facing and we can change the threshold and see it. So how it's done, it's actually a little tricky to do it. So let's start by explaining what we actually want to do. So let's imagine that this is my x-axis, and on this x-axis I have my pieces. So I have maybe 4 boards instantiated, and we know that we set up our geometry so that it's copies from the positive x-axis. So our geometry starts copying from here. So let's imagine this is our pivot that we're starting to copy to, like that. And if we go ahead and try to rotate our geometry for every instantiation, we're going to, well, if we rotate every one of them, that's going to be fine because of the because let's say I want to go ahead and take this geometry and start to rotate 180 degrees. There is going to be problem if this geometry is also not rotated. It just means that we're going to start to intersect each geometry with itself, and this is not what we want. So what we want to do is basically make sure that any geometry that we actually want to rotate it up rotate, we want to first of all move it to the next point. Basically, what I want to do is, let's say I have randomized that this piece is going to be rotated. What I want to do is move this point to the width of this geometry to forwards, and then rotate it. And that would mean that there's a space exactly for this piece to be rotated around like that. So this is what I want to implement. Let's try to do this. It's going to be pretty simple. So, well, it's a little weird. So first of all, I want to make sure that I get my width, so my piece. So from our switch node, we have our widths, which we basically get from our dictionary. And then we also created our path deform. And our path deform is going to change the widths. So we did our measurement and we set our scale, which is just a multiplication of the parameter of our width dictionary parameter and the new width of that our path deform created. And from here we want to actually go ahead and start and add another attribute, which is going to be, I call this a rotate offset. And this rotate offset is multiplication of our parameter, which we got from width dictionary, multiplied by the scale, because this is going to give us the actual space with the scaling applied, what we are actually taking, what this piece actually takes on our end curve. So this is important for us to also multiply it by scale, because our scale is going to change based on our path deform. Once we have done that, let's go to actual implementation, which is inside here. And it's pretty simple. We basically want to make sure that we are not doing it over the last point, because if we are, because this logic depends on that there is a next point to look the direction at. So let me go ahead and do this. So let's say we have point 1, 2, 3, and 4, and basically all of them are reaching to the next point. And if we are at the last point, well, we do not have anything to look at. So we could look at back of it and invert the vector, but I didn't really bother to do that because it doesn't really matter for the one for the last point to be rotated or not. But for the rest of them, we want to basically get the direction of the so let me get this a little bit better drawn out. So we have our points, they are looking at the next one. What I want to take this point, get my attribute that I created, rotate offset, and move it by that amount to the next point, which is done by getting the position of the next point. So we have our current point and our next point, and we want to get the direction that this vector is going to point to, which we can do this by subtracting next point from the current point. We have gotten this vector, and this vector we want to normalize it to the 1, so that it's 1, length is 1, and we just want to then multiply it by our rotation offset, and this is going to give the actual move it by the actual size of the geometry that is instantiated. And then we just want to add this amount, this vector, to our current point, and then we want to invert our normal attribute, which is actually responsible on which direction we actually copy our geometry. So take a look at the geometry which I'm instantiating, which is this one, and I think it's basically a z-axis. So you can imagine that our normal, which is actually responsible for the side on which direction the geometry looks at, looks at the positive z-axis like that. That's why everything points to the same direction. But if I invert it, it's going to look at the other direction. And this is where the orient along the curve comes in handy, the normal attribute. Like that. You can see beforehand, we are all looking at the same direction, and after that, and after this one, you can see we have actually randomizing the direction we are looking at. And you can also see that some of these points are actually moved beforehand. You can see this point, it's actually now moved downward. or upwards, depending on the curve is on which direction curve is looking going to. So, but at the end of it, we should have a very simple way for us to rotate it like that. So that's that. So this is mostly all I wanted to show inside Houdini, and there is a lot of ways we can improve all this. But I wanted to show how to deal with geometry that is not ideally aligned along the x-axis. So inside Houdini it would be pretty straightforward for you to do that. But let's go ahead and take a look at how to do it in Unreal Engine. So in Unreal Engine, what I want to do is I got this plank which I actually want to go ahead and reload. There's like where's it? Asset, actions, reload. To reload. So you guys are going to give it. You can see that I have this board, but it's in pretty bad shape because if I start to instantiate this one, it's not going to look very well because it's first of all it's sideways. And the x-axis is along this axis. So what I want to do is change the pivot inside Unreal Engine, and this is done pretty simply. So what I want to do is drag this plank out and go inside Unreal Engine. I want to go to the modeling options. I want to X-form and I want to transform. I want to go ahead and rotate it around 90 degrees. So this, I can move it upwards, but you have to look at this pivot. So I have now rotated it, and I want to change the pivot location along the x-axis. I also want to make sure that my geometry is now that this is also along the x-axis. So x-axis will be the red one. So just rotate it 90 degrees. Like that. This should be 0. So 90 degrees, now we're looking perfectly on the x-axis. And now we have to change the pivot. So now and the pivot is changed with the X transform with the edit pivot. So I want to complete the transformation, edit pivot, and just go ahead and move it on the side, at the end of the geometry. So it's kind of hard to look. You can try to check these center, left, front, back, like that. So basically I just want to move this upward like this, and I want to make sure that it's also in the center. So this is a pretty much ideal pivot for me to copy along the x-axis the geometry, accept. And one thing to make sure that you want to save these geometries for your static meshes, because right now we have just moved the pivot, but we have not saved it. What you can do is go ahead and say bake transforms, accept, and that's it. You can see the thumbnail changed, and we have now realign this geometry along the x-axis. That's going to work very nicely for our tool. So another thing that I wanted to showcase is actually our controls on the width override where we created, because we do not have to create this geometry specific width of it. What we can do is actually overlap them and rotate them. Let's take a look at how it would actually look like. You can actually get pretty weird results with it. So let's say I want to change the width of these pieces actually a lot smaller than they are. So instead of 0, maybe something like so right now it's 0.2. I want maybe something like subtract 0.15 from them. It's going to make it overlap very a lot. But what we can do is actually go ahead and increment the pitch, yaw, and roll of these. You can see we're getting really weird results right now, and it's basically this geometry. This tool doesn't have to be only for the fences. It can even be maybe it can even be renamed, to be honest, because I definitely can see the different use cases for it. Actually make it subdivision curves like that. See, we can get some really weird results with it. So, and obviously we can at the beginning of this tutorial actually try it out with the with like geometry that I had with something like these tombstones and all of this geometry, which we can just go ahead and try to reference instead of this. Let's try to reference these. So you can see we are getting a little bit weird results, but this is probably because of these. Probably want to rotate a little bit less than them. Definitely want to random piece spacing. We want also random deletion, maybe like a half of them, like that, and random seed, like that. So obviously we cannot guarantee for these to intersect because of these pivots can be wildly different. You can see inside here they are at the middle of it, so that means that once you copy it, there is a possibility of overlapping of them. So other geometry is at the sides of it, so it really depends on the geometry that you want to instantiate. So, but this doesn't really doesn't mean that we can't check for intersections. We can definitely use the tool that I showcased in my previous video, where we basically inside Houdini checked for intersections and deleted the intersected geometry, something like this, which is probably not that big of a deal. Or we could fix it with the pivots. So what we could do also is we could basically fix the pivots inside Houdini and then copy it and then fix the pivots and then offset it with the pivot information. Well, that would be quite involved process though. So yeah, but there is a way for us to also fix the intersections, and there's definitely a lot of ways that we can improve this tool. And before I end this tutorial, I wanted to show one or two things more. So first of all, this pattern tool that we created, which sadly I didn't really realize when I created this, it doesn't really work inside Unreal Engine because of the pattern, because of the pattern, where is it? Pattern, basically the pattern tool is actually, well, it doesn't really pick up any of this geometry inside here. So let's say we have input this geometry. Let's go to the Houdini. Let's take a look at it. And let's say I want to create a pattern. So inside here, my parameters, I want to randomize. I want to create a pattern. Inside pattern, I go ahead and create a tombstone and torch large. See, we have our pattern. Let's actually go ahead and random delete, random facing node, random delete 0. You can see we have our pattern, which looks fine, and it's being created. And also, I think it's also inside Unreal, should work just fine. But there is a problem because we can't really select the pattern within Unreal Engine. This tool doesn't like these parameters, doesn't like this menu that we created. So yeah, so this works only inside Houdini, sadly. So you can still, if you have Houdini session sync, you can create the select the pattern inside here, and since the parameters are actually synced with Houdini, you can go ahead and see the results of the pattern inside Unreal. So this is one downside. So probably the best way for us would be use a pattern of something like integers. So you could probably start assigning integer values to these multi-parameters and just visually see the pattern that we want, and then just write like a 2, 1, 2. This would be our pattern, and you would see it, and it would be able to write it inside easily with simple integers inside here without writing the name of the meshes. So this is definitely a place to improve this tool. So yeah, I just wanted to note that, yeah, sadly it doesn't work with Unreal Engine, this parameter. Shows actually for the size axis to work properly. You can see if we put on the x-axis, it's aligned like that, and z is aligned along the z-axis. It's actually, we have to make sure that our path orient along the curve is actually there's a instead of is it, so it's a yaw. So it's a yaw. So let me take a look at the result. Let me, in this path, the yaw parameter, which is actually let me copy this and let's put it on a 0. So the yaw parameters actually determines how the geometry is rotated. You can see you can basically see that it's rotating around its pivot, which is around here, the x-axis around here, like that. And what we want to do is make sure that it follows the x-axis parameter. So if we have our x-axis, we want to make sure that our yaw is basically these parameters. If the CHS size axis equals 0, so basically if it's 0 x-axis, we want our yaw to be 0, but if it's a z, we want to rotate it by negative 90 degrees. So these are just the values that I saw that work out, but it is important for that our orient along the curve does know on which direction to rotate this geometry. So this is one thing to definitely do if you have geometry that is align the x-axis, because actually by default we actually use x-axis, which needs a negative 90 degrees. By default the z-axis would be 0. So yeah, so this is definitely one last thing to note. So yeah, but I think this is going to end this tutorial. This video has gone a little too long, to be honest, but yeah, I hope you learned something and see you next time.